assuming you are all from BSc, BTech students must not have done this, but linear harmonic oscillator you all may have studied in your undergraduate or postgraduate courses, right? So what I'm going to do is that since we need to see various approaches of understanding this problem, we will not go to all minute details, but yes, we can stop and discuss those details if there is a question which is of fundamental concern, right? So that's what I'm thinking. There are two, three things that we can see in linear harmonic oscillator cases. Some of you may have seen it, most of you may have not, because we generally use in our curriculum, it is the Schrodinger picture which is there. So that is the whole purpose. And today I will also give a few exercises as well. I hope you were able to solve the exercise that was given yesterday.
Yes, sir. Yes, sir.
Okay, excellent. Fine. So now I'm going to share the screen, and I think 10 participants are there, 7 are online. So I think majority 10 plus 7, 17 students are already there. We can begin. So yes, let's go ahead with a linear harmonic oscillator. Now, if we do it perfectly step by step, even in the Schrodinger picture, it takes around at least 7 to 10 pages of derivation, right? So I will be going through very important aspects only. And if you need, we can share notes that even some of the book have these derivations, and you can try at home. And we can also share class notes that we teach to our students at the end of the lecture as well. Okay, so you may see certain jumps, but they are necessary jumps to cover the particular aspects that we are intending to. Okay, now, so simple harmonic oscillator, right? We know it from our 11th, 12th standard physics, right? Okay. Now, if we look at the potential of such linear harmonic oscillator, it is given by Vx is equal to half kx square, right? And if we are looking at the Schrodinger picture first, so let me write here. First, we'll go through Schrodinger picture. Also, I will share the PDF of last class's handwritten notes. Okay. So yes, remind me at the end of the class. So I will share immediately today. Yes, so if we write the Schrodinger equation, it will be minus h cut square upon 2n d square by dx square plus half kx square operating on psi of x, which is going to give us e psi of x. Okay, we get rid of this minus h cut square by 2m to have second order ordinary linear differential equation. Okay, and that will turn out to be d square by dx square minus mk upon h cut square x square plus 2me upon h cut square psi of x is equal to 0. Okay. What is the aim? So if we keep on giving the equation some number, so we don't have any confusion. So let's call this 1, this is 2, and this is 3. Fine. So what we are intending to do is that we are intending to find the solution of this differential equation that satisfies all condition which is good for our wave function psi. Right? What are they? It must be single valued, it must be continuous, it must be differentiable, and it must be finite everywhere. Okay, fine. Going ahead. Now, what we will do is that here we need to make a variable change, right? To make the equation quantity to have a dimensionless aspect. Okay, so what we will do is that I will have a some quantity assumption that let this mk upon h cut square be alpha. Okay, so if alpha is mk upon h cut square, and if I assume its power to be 1 by 4, Fine. And if I substitute the value of k, it will turn out to be under root m omega upon h cut. What is the k? M square omega square, right? In simple harmonic oscillator. Uh, and this alpha, it has to be dimensionless, right? So we assume that this alpha, if I multiply it with some x, I am really skimming so many things. That's why it's slowing me down. Uh, but it is necessary, right? So you need to assume this particular aspect. And then we say that our psi x, that is our state vector, is the component or function of chi, where chi is alpha x. So you can see x has a unit of centimeter or meter, right? So what is the unit of alpha if you can check? Meter inverse. Okay. So here phi chi is now getting substituted at the place of psi x. Fine. Uh, Going ahead, the entire differential equation then changes to alpha square d square by d chi square minus alpha square chi square plus 2me upon h cut square phi of chi is equal to 0. Okay. You simplify it further, we get rid of these alpha squares here, right? So ultimately, a simpler form of this equation will be d square by d chi square minus chi square plus 2e upon h cut omega function of phi chi is equal to 0. Okay. Now, again, you must have studied Hermites polynomial, right? So what is the structure of Hermites polynomial? It is like this. Let's say Hn is some Hermite polynomial function, right? So it is like d square Hn by dx square minus 2x dHn by dx plus 2n Hnx is equal to 0. This is a Hermite's differential equation, right? So from the comparison of the above differential equation and with the help of Hermite's orthonormal function, I am talking about Hermite polynomial's orthonormal function, not Hermite polynomial itself, right? Okay, so that's a difference. Uh, so Hermite's polynomial and its a function and its orthonormalization, that all comes under a very separate discussion, which is, I think, it's a special function. So it requires totally different discussions. We can go through it if time permits at the end of the lecture. Fine. So phi and x, right, is one of these Hermite's orthonormal function, which is given by 1 upon under root pi into 2 to the power n into n factorial to the power 1 by 2. And here in the numerator, we have the power of e to the power minus x square by 2 into h and x. Right? So what can be inferred here? Okay, we have not given equations again. Fine. I'm not good with the numbering. So let me point out the equation that I am talking about. So here, this is our differential equation, right? So where we began. So if you will see in the books or your notes or during your undergraduate classes, you can see that from here and this, we can confirm that this is a possible solution, right? If there are certain discrete energy levels, right, such that it has to satisfy that 2n upon h cut omega is equal to 2n plus 1. I'm really sorry for skipping so many steps, right? But we have very little time. And at the end, it turns out to be that the energy is n plus 1 by 2 h cut omega, right? Where n's value vary from 0 to infinity. And hence, when you substitute n is equal to 0, it is also called 0 point energy, because at n is equal to 0 level, that is ground state, or you can say that it still has some energy, that is half h cut omega, and hence it's also called endpoint energy or 0 point energy. Okay, that's also very well known. Going ahead with the so this is important quantum mechanical aspect of endpoint energy, right? You know that very well. Let's focus on our Eigen function. So this phi and x, now if I write in the form of phi and chi, right? So then if I rewrite it, its structure will change a little bit, right? Otherwise, other terms are going to remain the same. That is under root pi into 2 to the power n into n factorial into e to the power, instead of minus x squared by 2, we will write minus chi squared by 2 into hn chi. Right now, it's an, what did I say? It's an orthonormal function of Hermites differential equation. Okay, this phi n is the orthonormal function of Hermites differential equation, and that function here, what it is representing, the Eigen function for our case. That means it must be, or it can be normalized in the way we normalize state vectors, right? So that means if we normalize it, the normalization will be phi n star chi, let's say some state phi m chi d chi del nm. Fine. Now, if the function were psi x, if our state vector was psi x, we would have normalized it in sin star x, psi mx, dx. Okay. And in that case, just to show you, this will be my sin x instead of phi n chi. It will be under root alpha, because chi is substituted as alpha x. Fine. So under root alpha will come up. Let me remove this. So it will be under root alpha under root pi into 2 to the power n into n factorial to the power 1 by 2 into e to the power minus alpha square x square by 2 into hn alpha x. Okay. So what is done using Schrodinger picture? We have now obtained the eigenvalues and eigenfunctions for linear harmonic oscillator. So this is your eigenfunctions, means this is the state vector that we are talking about for our picture, which varies over time, not our dynamical variable in Schrodinger picture, right? And this is the eigenenergy equation for the same. Okay. So this is what you have done in your BSc program or MSc program. You have solved it much more in details. Many steps are involved. But now we are moving towards our interest. This is everyone has done. Now let's move to what we are intended to do, the Heisenberg picture. Okay. So what is the Heisenberg picture? Let's hear from you.
In terms of operators and matrices.
Right. But the in Heisenberg picture, remember, the operators are time dependent, right? And state vectors are time independent, are not time dependent, or in other words. Okay. Okay. And also remember, what did we discuss in the last class? That Heisenberg state vector coincides with the Schrodinger state vector at time t is equal to 0. Remember that?
Yes.
Right. So keep that in mind. Now, with that thing in mind, that Heisenberg state vector is coinciding with the Schrodinger state vector at time t is equal to t0. Now let's write the Hamiltonian. Okay. Now here the Hamiltonian will be time dependent, right? And how do we write the time dependent Hamiltonian? That means, what is the Hamiltonian? Kinetic energy plus potential energy. That means my P is function of T, right? Square by 2m plus half K. Now, K will not be time dependent. It will be X, which will be time dependent, right? So I can write it like this, xt square. Okay. So here our dynamic variables are P and X that we are observing over there. Fine. Simplifying it, I can rewrite it as 1 upon 2m P square function of time plus m omega square, sorry, m square omega square, K is m square omega square, X square function of time, right? Now we are in Heisenberg picture. Operator is time dependent, right? And its rate of change is given by the relation that we saw yesterday, right? What was that? dA by dt is equal to 1 upon IH cut, commutator relation between A and H. Remember?
Correct.
Right. So here we will use the same. So it will be now a commutator relation between, let's say, first let's take X and the Hamiltonian H, right? So our dynamic variable X operator is what we are using. So it will be dx by dt is equal to 1 upon IH cut commutation between, X and H. Okay. Now, what is the operator correspondence for our dynamic variable X in quantum mechanics? It will be IH cut del by del P, right? So if you use it, what will happen to the next step? What will I get? I want answer from you. You can take few seconds or minute.
2IH pi.
2, where the 2 will come from?
The first, that if we expand the Hamiltonian, the
Hmm.
commutator of X with P will
No,
be.
no, no, no. We will not write these particular terms right now. Okay, let's hold that. Okay.
Okay.
Anyone? You will be left with simply, if someone can give me the answer, del H by del P.
Yes.
Right. So in general, what is my dx by dt? Velocity, right? We have relation p is equal to mv. So I can write that this is p by m. Okay. Similarly, if I use this relation for my second variable, that is p, you will have your dp by dt is equal to 1 upon IH cut commutation between p and h. Now, what is the dynamical variable p in quantum mechanics? It is minus IH cut del by del x, right? Give me the answer.
Minus del H by del X.
Excellent, right? Which will turn out to be, what is dp by dt again? Yes, you all know this. Very simple.
But that is Kx, potential Kx.
Excellent, right?
Yes.
Perfect. So that means I can now use these results, right? What are these results? So let's write, I have dx by dt. Fine. This is my first result. Let me zoom it out. I have this second result. What do you think we can get from this equation? Okay, so okay, let's not waste time. We have exactly, I think, 40 minutes. So yes, if I differentiate dx by dt one more time, it will be d square x by dt square. It will be 1 upon n dp by dt. What is dp by dt? Minus m omega square x. So it will be simply minus omega square x. Where did it lead us to? So this equation is nothing but d square x by dt square plus omega square x is equal to 0, which is well known or identical equation to classical equation of motion of linear harmonic oscillator. Correct?
Sir,
Huh?
sir, इधर मतलब b equal to minus I h का del by del x से minus del h by del x नहीं आ पा रहा है.
You are talking about del p by del t.
The last third step. dt.
આવડું
એના ઉપરનું sir.
શું આવશે તો? What will it? Let's keep it in English. What it will be?
So like from commutator of p and h, we
Mhm.
get del h by del x by using the operator.
થોડું નજીક આવીને બોલીશ. Can you speak coming closer to the mic? Yes. થોડું that there's some disturbance coming in between.
Sir,
Yes. Huh.
from commutator of p and h, using operator correspondence, we can't get minus del h by del x.
What we will get? You are not sure.
I'm not sure about that, sir.
Okay, fine. Mhm. Hello.
Okay, sir. Like we will figure it out.
Yes. So let's keep this discussion part for the later, right?
Right.
But this is the result that you definitely get, right? We have not seen the commutation with Hamiltonian. That's why there may be some confusion, but we can discuss it later. Remember, but Hamiltonian we consider to be Hermitian. Okay.
Yes, sir.
Yeah, keep that in mind. Now going ahead with this d square x by dt square, this is like classical equation of a simple harmonic oscillator. Okay, what is the solution? We all have gone through this, and the solution is given by xt is equal to a1 cos omega t plus a2 sine omega t, right?
Yes, sir.
If we differentiate it, dx by dt, it leads us to minus omega a1 sine omega t plus omega a2 cos omega t, right? We can determine these constants a1 and a2. How do we do that? Simply put the condition at t is equal to 0, right? So you will find that a1 is nothing but x at t is equal to 0, x0. Okay, or we can simply write x0. Fine. And then from dx by dt, integral for t is equal to 0, right? We can say that our omega a2 will turn out to be p at t is equal to 0 by n. Okay, so how did we get here again? Don't get confused. It is from dx by dt relation, which is we just did. It's del h by del p is equal to p by n. This one. Fine. Okay. I'm just going through the some mathematical aspects which can be derived at ease by yourself as well. Okay. So this is the first constant a1, which is x0. A2, it will turn out to be then from here simply p0 by w omega m, sorry, omega n, p0 upon m omega. I will write it like that. Fine. So we can now substitute them in the equation of xt, right? So it will be simply xt. It will be x0 cos omega t plus p0 upon m omega sine omega t, right? Similarly, we can have p of t. This is very simple, p m dx by dt only, right? If you do that, m omega will, you can keep m omega out from here and the first term, and what you will be left with is p0 cos omega t minus m omega x0 sine omega t. Fine. Okay. So what does this say is that it means that from this term that harmonic oscillator is a case of stationary state problem, right? And we can show that Hamiltonian is independent of time. How? Okay. So what will be the Hamiltonian? It will be kinetic energy plus potential energy. So I will use this term and then I will write this again, p square t plus m square omega square x square of t, the Hamiltonian we begin with. Fine. So let's see whether it's a time independent or not. Over here. We did write it somewhere. Yes, I think here. This part. Okay. Going ahead, if you substitute them, the xt and pt value in this equation, right? You can do it. I am simply writing the output that you will get. It will be 1 upon 2m p0 square plus m square omega square x0 square, right? Now, be focus on my words. This is where we move to the entirely new aspect, right? Okay. So here we have p0 square plus m square omega square x0 square at t is equal to 0, right? Which the Heisenberg state vector is borrowing, or we are using one borrowing, but it is coinciding with the Schrodinger state at t is equal to 0, right? So Hamiltonian is time independent. But how do we obtain energy level of harmonic oscillator? That is our next challenge from this Hamiltonian, right? So what was done is that a Hamiltonian matrix was created. Right? It is generally it is written as H n dash n. Right? It was we have to construct such matrix which gives us complete set of orthonormal function, right? And then we have to diagonalize it. Now, why diagonalization? Can someone tell me? Now, okay. Before someone answers that, what is our state function? Our state vector state function or wave function is psi nx. I will call it psi nx since we are giving the suffix n, right? So psi nx is our state vector in Schrodinger picture, right? At t is equal to 0, okay,
Yes.
which is coinciding with our Heisenberg picture, right? And then it's Hamiltonian, which we are trying to write in Hamiltonian matrix form, right? So see, if psi nx, if we choose a complete set of orthonormal function, then the Schrodinger picture, which is coinciding with Heisenberg picture, will diagonalize the Hamiltonian matrix. So, okay, let me write the H n dash n in this particular form again. 1 upon 2m. I will separate the terms. At t is equal to 0, p0 square n dash n plus half m omega square x0 square n dash n. Now, what is this p0 square n dash n and what is this x square n dash n? It's very simple to see, right? So if I show you p0 square n dash n, you already know all this thing, just that we are putting all the pieces together, right? You know what is the correspondence for p? It will turn out to be minus IH cut square integral minus infinite to plus infinite psi n dash x. You keep this, you remember this and keep this in mind. Okay, in previous class as well. I will shift this a little bit. We need some space. Okay. D square by dx square sin x dx. Agree or not?
Yes, sir.
Fine. Now we simply use the fact that alpha is under root m omega h cut square, right? And the alpha is already there in x and chi, it is hidden there, right? So if we want to move from x to chi, right? So we are now moving from x to chi. It will be minus h cut square alpha square integral minus infinite to plus infinite phi n dash chi d square by d chi square phi n chi d chi, right? Now remember the relation with Hermites orthogonal function, right? So I will use that. It transforms this equation into h square alpha square minus infinite to plus infinite. I'm getting rid of the minus sign, right? Phi n dash chi, this turns out to be 1 plus 2n minus chi square. Those who are familiar with Hermites polynomial and its functions, they can appreciate this, right? Okay. Otherwise, it is fine. You can go through the Hermites polynomial and its function separately as well. And the result that this particular integral gives us is very interesting. It's going to give us, this is h cut square alpha square into 1 plus 2n del n dash n minus alpha square x is 0 square n dash n.
Yes.
Right. Now, what is alpha square? Alpha square we know is m omega upon h cut. Fine. That means h cut square alpha square upon 2m is our half h cut omega, and h cut square alpha to the power 4 upon 2m, it will be half m omega square. You see the connections? Okay. So now what we are going to do is that we are going to use these, and we are going to substitute it where? In our HNN equation. Can you do this? So if I do this all substitution in this, let me give it a box. If we do all these substitutions, right? So, okay, let's do it step by step. So what is the first component in HNN? 1 upon 2m p0 square n dash n, right? Fine. Then half m omega square x0 n dash n. So it will turn out to be, if we substitute all this term, h dash, or sorry, not h n dash n is equal to 1 by 2 2n plus 1 h cut omega into del n dash n minus 1 by 2 m omega square x0 square n dash n plus half m omega square x0 n dash n, which will give us or lead us to further simplification. What is left now? you can simply see it's only left n plus 1 by 2 h cut omega del and dash n.
So last में x0 square है ना?
Ha. Okay. Sorry. Fine. So what we obtain the eigenvalue from the Hamiltonian, it is simply from h and n, which will be n plus 1 by 2 h cut omega. Right? For n is equal to 0, 1, and so on. Now let's go back to our Hermites orthonormal function, because that's what is going to give us our dynamic variables, right? Where they stand and how do they look like in the form of matrix form. That's where we are heading now. So once we have this, so okay, so how does the matrix look like actually? You may ask, right? So it will be like this. It will be H is equal to H cut omega by 2. This is a giant matrix, but I will just go for some terms only. For n is equal to 0 and so on, right? For next, it will be 3, right? 0, 0, 5, 0, 0, 0, 7, right? And so on. So it will head down diagonally like this. For n is equal to 0, 1, 2, and so on. So you can see it's an entire trace of the matrix, right? Which gives you the all the energy levels, discrete levels. Fine. So moving ahead, I was talking about Hermites orthonormal function. Sorry. So let's again focus on phi and chi. Right. So what was our phi and chi? Schrodinger equation 1, right? That we can use because that is same for Hermite, right? Whether you are using Schrodinger or that. So that was 1 upon under root pi into 2 to the power n into n factorial e to the power minus chi square by 2 into hn rho, right? Now, if you look at the orthogonalization condition for this function, then again, I can share the notes for Hermites polynomial where this is derived very well. Fine. Those who are going to study or those who have studied special function will appreciate it later. Okay. So 1 upon root 2, it will turn out to be 1 upon root 2 under root n into del n dash n minus 1 plus under root n plus 1 del n dash n plus 1. Right? You can do this in Schrodinger case. You get this in Schrodinger case. Can someone tell me how do you get it? These are nothing but your selection rules, kind of. This provides you the selection rule for simple harmonic oscillator that what levels can be occupied, right? Can someone tell me how can you find, how do you find the same equation in Schrodinger picture? Anyone? Anyone?
So by scalar product of
Yes.
functions and then of obtaining the differential equation, it was presented, right?
Right. So you can use the, of course, you need to take the help of Hermites polynomial and you can use it as he said, and you will find the relations, right?
उसमें मतलब उसके properties use करनी पड़ेगी ना Hermite polynomial.
बिल्कुल. So that's what I am saying. Hermite polynomial, please engage yourself with Hermite's polynomial today, right? You go through its recurrence relation, okay? Then you can go through its generating function and then the orthogonality. Now, orthogonality and generating functions are related, right? that it satisfies its orthogonality relation if it has certain generating function. So it's very elegant and interesting. It can take up more than 2 or 3 lectures on the discussion of the polynomial itself. Fine, that's why I have avoided discussion on Hermites rather than focus on the methodology. Okay, so similarly, so yes, so what happens to the orthogonalization condition? It follows further that phi n dash chi and phi dash n chi, right? It turns out to be 1 upon root 2 under root n del n dash n minus 1 minus under root n plus 1 del n dash n plus 1. Okay. The point is, this is the secondary one is not necessary. This is the very important one. If you look at here, from this, you can follow that your x0, because chi here, right? What is chi? It's alpha x, right? So your x0 matrix at time t is equal to 0 can be found from them. It will be x0 n dash n. Let me remove this. It is not required for right now. Okay. So if you go look at from here, you substitute chi is equal to alpha x, and this entire transformation will happen in this form under root 2 alpha under root n. Other terms almost remains the same, right? N plus 1 del n dash n plus 1. Okay, so this is alpha. We know what is it? M omega upon alpha square is m omega upon h cut square. Okay, so it will be under root h cut upon m omega under root n del n dash n minus 1 plus under root n plus 1 del n dash n plus 1. Fine. Similarly, you can find for P0 n dash n, which is minus IH cut phi n dash chi d by dx phi n chi. Okay. Minus IH cut, okay, it will turn out chi is alpha upon x. It will be alpha phi n dash function of chi d by d chi phi n of chi expectation value, and you will find that it will be minus I under root h cut m omega by 2 into h cut m omega by 2 into under root n del n dash n minus 1 minus under root n plus 1 del n dash n plus 1. Fine.
Yes.
And the matrices will turn out to be for x0 and p0. They will be like this. x0 will be under root h cut upon m omega. I should have written it just below the equation, but let me just scroll down, right? Here. Okay. Oh, I missed the 2 over here from the equation. Root 2 is there, right? Fine. So under root x0 h cut, so it will be under root h cut upon, let me rewrite it, 2m omega matrix 0 under root 1 0 0 under root 1 0 root 2 0 and so on, 0 root 2 0 root 3 0 0 root 3 0 0 and so on. How did we get this value? You can substitute the value, right? So that's your x matrix, and the second variable, that is p0, right? It is again I is there, but we will keep the I out. We will not put it in the matrix. So keeping the negative sign, no, we will not keep negative. I under root m h cut omega by 2. The matrix will be Let me have some more space. 0 minus root 1, 0, 0, and so on. Root 1, 0 minus root 2, 0, 0, root 2, 0 minus root 3, and so on. 0, 0, root 3, 0. Now you can check any element from this equation, and you will find that it fits perfectly well. So these are now your three matrices, right, of Hamiltonian, your dynamic variables, x zeros and p zeros. Now remember, matrices of x0 and p0 are not diagonal matrices, right? Only your Hamiltonian matrix is a diagonal matrix. So what does it say? The matrix of x0 and p0 are no, they are non-diagonal, right? And also remember their expectation value. What will be their expectation value? X zeros and p zeros at t is equal to 0. You can tell it directly.
Sir, X and P's are Hermitian, right?
X0 and p0 I'm talking about. Yes, they are Hermitian.
Yes.
So at t is equal to 0, their expectation values are 0.
Yes.
Right?
Yes.
So now since it's a Heisenberg picture, we are representing dynamical variables by matrices. And this method is called matrix mechanism using Heisenberg picture. There is one more method. So we have seen two methods. There is third method. We will quickly look at the method. I think I know one person know. Two of you know this method because it has been discussed in a class. It's by Dirac, right? It's called, oh sorry, method of second quantization. Okay, so when Dirac was looking at the field quantization, right? So he used this technique in anticipation of field quantization, right? And that's why it is called second quantization method. Okay. The consideration is that the energy levels of simple harmonic oscillator are equally spaced. En is equal to n plus 1 by 2 h cut omega. The difference is, you know that, right? The difference is equally spaced. It's uniform. So we can characterize energy levels as phonon levels, right? Where you can assume that positive integer values are assigned from 0, n is equal to 0, 1, 2, and so on. So any excitation, de-excitation that occurs is like occurring between n is equal to 0 to n is equal to infinity, right? So that's, so are you understanding where we are going? That where he was going, actually, this is Dirac's method. So what happens is that when there is an excitation and when there is a de-excitation, there is a creation and annihilation of the phonon, right? So in the phonon and photon corollary, or what we can say analogy, is used many times. Here it is used for the phonon, right? That we have E is equal to n plus 1 by 2 h cut omega. N is from 0, 1, 2, and so on up to infinity. So phonon vibration have excitation, de-excitation, and they are between this 0 and this number. So whenever there is excitation, there is a creation. Whenever there is de-excitation, there is a annihilation of phonon. So they are acting as an operator for phonon. Are you understanding this? So what was done was the two operators A and A dagger were defined, right? Now operator A was defined as 1 upon under root 2 m h cut omega m omega x0 plus ip0, and A dagger was defined as 1 upon, sorry, I need more space, was defined as 1 upon under root 2 m h cut omega. Numerator is different, m omega x0 minus IP0, right? So if you add and subtract these two equations, if you add and subtract them, you can obtain x0 and p0. What you get from here is that you get them in the terms of A and A dagger, right? The operator which defines where excitation and de-excitation of phonon is happening, that is creation and annihilation is happening, right? Just like a simple harmonic, because phonon have oscillations. I hope you are getting this idea. Some of you may have seen this, some of you may have not. Under root h cut upon 2m omega, it will turn out to be A plus A dagger, and this is going to be I under root m h cut omega upon 2 A dagger minus A. Right? So if x0 and p0, if we identify them as operators, because what they're dynamic variables, right? And how do we deal dynamic variables? We consider them as an operator, right? That means they should obey their commutation relations. What is commutation relation between x and p? In this case, x0 and p0. I h cut, right? What is the relationship between x0 and x0? 0. P0, P0, again 0. Right? So you can simply see that the commutation relation of this dynamical variable operator, right? What does it yield is that it provides us a commutation relation between annihilation and creation operator. Okay, so that means it provides us a relationship between A and A dagger. It turns out to be 1. See, there are so many intermediate proofs that you can do, discussion we can do, but we are focusing on the methodology. And A dagger, again, it gives us 0. Now you can see how they are annihilation creator operator. They are behaving just like our position and momentum dynamic variable operators. The commutation is 1 in the case of operators that are annihilation creator operator. In case of x0, p0, it is IH cut. Right? Now let's write the Hamiltonian that we know. The Hamiltonian is 1 upon 2m p0 square plus m square omega square x0 square. Right? If we are expressing the x0s and p0s analogy between A and A dagger, we can rewrite this again as Hamiltonian being half h cut omega A dagger plus A dagger A. Fine. Now, here we know this relation A dagger is equal to 1. So I can use this to rewrite the first, because A dagger means A dagger minus A dagger A is equal to 1. Correct?
Yes.
So I will use that 1 by 2 h cut omega to write this as A dagger A plus 1 plus A dagger A. Correct? From this relationship.
Yes.
Okay. Okay. Simple. So this is turning out to be h cut omega n plus 1 by 2. So what I have done is that I am calling this n as A dagger. Right? So you can verify that this n or A dagger itself is a Hermitian operator. That means the n that I'm talking about, n dagger is equal to n. Okay. See, there are so many minute things. It can take many lectures, but pardon me for being too fast and rushing to cover the aspects, right? So you can prove that it can be verified that this is a Hermitian operator n itself, right? Okay. And it will have real eigenvalues. Fine. So our operator n is known as our number operator because we know that it's n. It's relating to the states. So if we find the commutation relation of this n with A and A dagger, what do you think it will be? Any guess that since n is analogous to our n is equal to 0, 1, 2, and so on to infinity, right? Then if n is with a, it gives you minus n. When it is here, it gives you 8 dega.
सर उल्टा नहीं होगा
उल्टा मतलब
एक सेकंड सर
you mean a? No, 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 no. I think this is how it will go.
नहीं मतलब मैं माइनस और प्लस का बोल रहा
Uh,
हूँ हाँ
maybe I may have made a small error. I need to check as well.
नहीं ठीक है
No, I think it is fine. Huh?
हाँ सर ठीक है
Okay, fine. So yes, so what we are discussing. So the next task is that we need to find the normalized eigenvectors, right? So let's say phi n is our state vector phi n. So if n phi n is operated on phi n because it's an Hermitian operator, right? It's a number operator. Its commutation with a and a dagger, that is creation and annihilation operator, gives us minus a and a dagger. So then if it's a Hermitian operator, then a normalized eigenvector should give us n phi n, right? So n, small n represents eigenvalue. Okay. So using this commutation relation, we can show that a phi n and a dagger phi n are the eigenvectors, right? And they are corresponding to eigenvalues n minus 1 and n plus 1. Fine. Now, you can see that I am not going into the derivation, but if you want to see the equation, it is like this. When a and a operates on phi n, it is like this: a n minus a phi n, right? And it will turn out to be a n minus 1 phi n, and hence you have n minus 1 a phi n, right? So that's why a is associated with n minus 1. Similarly, you can show that a plus is associated with n plus 1. That means my a, what does it do? It reduces the state from to n minus 1, and a dagger, it increases the state to n plus 1. That means a and a dash are my ladder operator. One is raising the level, another is lowering the level. So that's why we call it, in another terms, creating an annihilating operator, right? So they are either adding a phonon or removing a phonon. Now let's consider the matrix element in here. Fine. So if you consider the matrix element, then the n can be represented as phi n and phi n. Now what is n? N is a dagger a. Right? This will lead us to a phi n, a phi n. True. So eigenvector a phi n is normalized to n. And similarly, if a phi n is normalized to n, right, then eigenvector phi n minus 1 is normalized to 1.
Plus 1. Sorry.
So it will follow that phi n minus 1 will be 1 upon root n a phi n, and phi n plus 1 will be 1 upon under root n plus 1 a dagger phi n, annihilation and creation. So how do we write matrix element for operator A dagger? So first, let's go from here. So this is for A dagger. Now let's write for A dagger, right? I am changing this to A dagger. What will happen? Let me write so you can have in the notes as well. So if I write it for the phi n A dagger phi n, it will turn out to be phi n A dagger A plus 1 from our property that commutator between A and A dagger is 1, right? Okay. Going ahead, this will be simply phi n plus 1. We just saw above here. Right? N plus 1. It's associated with that. So you will turn out to be n plus 1 phi n. These are all provable, not that much hard. Okay. So this equation, what does it give us? Just like previous one, the A dagger of phi n and A dagger phi n. Above we saw A phi n, right? This leads to n plus 1. Right? So normalized eigenvector phi n plus 1 can be given by this equation. Now that's what I justified now, right? So that's what both aspects are covered. Okay. How much time do we have? I think we have overshooting the time, but let me try to cover very quickly. So the point is that in similar way, if we keep on following a repeated application of annihilation operator A or a creation operator A dagger on eigenstate phi n, right? What you get is that you get a generic, if I write a generic term, then let's say n a to the power r phi n will be n minus r a to the r phi n, and n a dagger to the power r phi n will give you n plus r a dagger to the power r phi n. Right? So n can assume values differing in the terms of 0, 1, 2, and so on. Right. And finally, what you can write is that phi n dash a phi n, you can conclude to this, will turn out to be under root n del n dash n minus 1. Phi n dash a dagger phi n will turn out to be n plus 1 del n dash n plus 1. And if I write its matrix notation, then A will turn out to be 0 under root 1, 0, 0, and so on, 0, 0 under root 2, 0, and so on, 0, 0, 0 under root 3, and so on, 0, 0, 0, 0, and so on, and so on. Right. Similarly, A dagger, the matrix will be, who will tell me? 0, 0, 0, and so on. Root 1, 0, 0, zeros. 0, root 2, zeros, and so on. 0, 0, root 3, zeros, and so on, and so on. Right? And finally, n, which is A dagger A, fine. The Hermitian, its values will be from 0, 1, 2, and to infinity, remember? So all the diagonal elements will be in the terms of 0, 1, 2, 3, and so on up to infinity and so on. Now you can see the matrix representation of x0, p0, a dagger, and n using the Heisenberg picture and Dirac's second quantization method. Right? So these are the techniques that have been used. Now to understand them better, can I give you some problems?
Yes, sir.
Yes, sir.
Right? So using the creation and annihilation operator, you need to find using A and A dagger, that is creator and annihilator operator, find matrix representation of x0 square and p0 square. Right? So x0 and p0 are your position and momentum operator for linear harmonic operator. Remember it's x0, p0. Right? And also you can try some commutator relations, right? It will give you it will help you immensely, right? Having the discussion, or you try to discuss this commutation relation, what is happening when they are in commuting relations, what are the outputs. That's all. You can try this, right? Okay, and one more problem for ground state using the Dirac's notation. I'm giving it to you for, let's say, nth phonon state is there. For nth phonon state, cat n of simple harmonic oscillator or linear harmonic oscillator, the state vector is given by 1 upon under root n factorial a dagger to the power n cat 0. You know what is a dagger? A dagger is your creation operator for the phonon, and the cat 0 is the ground state, right? Ground state, right? So which is 0 phonon state of the oscillator, that is your endpoint energy, right? So you have to show that this is the equation for ground state, 0 phonon state of oscillator. Can you do that using the creation operator?
Yes, yes, sir.
Okay, so these are the 2-3 simple problems, and I can give the solutions if you require them, right? Very simple to prove. Okay. You can also try for various problems you can find in various books, where you can do the matrix representation of momentas and position. But here we did for t is equal to t0, right? T is equal to 0. What if time t is at time t I want to find? Can you do that? Think about what will be the xt and pt, not x0, t and p0, right? Let me give you the hint. Let me give you the idea of what will happen. You will see that when you do at some time t, when you do it at some time t is equal to, let's say, t dash, this will turn out to be under root 1 into e to the power minus I omega t dash, right? It will be into I to the power I omega t. It will be root 2 e to the power I omega t. Something like that change will happen. But you prove it that it will be in that form. Yes, you are getting it, right?
Yes.
E to the power I omega t, or here it will be to the power minus I omega t. So please, you can try that as well. Okay. Tomorrow we will begin with time dependent perturbation theory or interaction picture. Okay. Let's take a break. Enjoy your lunch. See you tomorrow, everyone.
And sir, like, can you share the notes?
Yes, thank you, Aziz. I will just share it in the form of PDF. I am sharing the notes and I will share it.
Also, sir, like, can you share the references for the code?
Okay, 100%. Yes.
Thank you.
I will share the books themselves.
Yes.
Okay, Gurudat sir. I think he's not there. Aziz, you can just stop the recording and end the meeting, and you all can proceed for lunch.
Yes, sir.